Continuing the story of advancing weather and climate forecasts, let's look at a couple of things, starting with the WMO's role in this whole business. I didn't read the history. It started basically in the 1960s, other than the international efforts that had started in the 1870s, as we saw before. So this is WMO designated Global Data Processing and Forecasting System Centers. Nowcasting to medium range prediction. Nowcasting is a very near real time, an hour, 2 hours, 3 hours, and medium range goes out to 3 to 10 days. Extended range is typically from weeks 2 to 4, what we call subseasonal forecasts. Okay, that depends on Madden-Julian oscillations and other predictable signals in the Earth's climate and weather system. So here are the places that I won't look at all of them, but India shows up here, and China is here, Hong Kong, of course Australia, and Pakistan. These are global data processing and forecasting system centers. So I won't read all the various levels of activities go on, and we will not worry about that. But if you look at India, it has 3 signals here. One is the I have to locate it. RSMC tropical cyclone forecasting. So India does cyclone forecasting, winter forecasting, marine meteorological services, as well as geographic specialization and so on. Pakistan, on the other hand, has marine meteorological services as the lone symbol there. Okay, there are others, Nairobi, Dar es Salaam. So everybody is involved, which is a good thing. Every country has realized the value of forecasts, and various levels of efforts are made. India, for example, gives its forecasts to the neighboring countries as well, and also trains them in using the forecasts. These are WMO designated data processing and forecasting system centers for long range to decadal climate predictions, and the number drops significantly here. So you have few in Canada and US, Europe, China, Japan, Korea, India, one center in IIT in Pune, and Nairobi, and of course Melbourne. So you go from weather to climate, different locations, so the foci can be different. Looking at the challenges and opportunities in the coming decade, recommendations. Operational weather forecasting based on numerical prediction systems has continuously improved over the past few decades. The usefulness of NEWP forecasts, ensemble weather forecasts, has been pushed to lead times beyond 10 days for some weather phenomenon, including for high impact events such as mid-latitude snowstorms in North America. As I said, predictability is longer in mid-latitudes because the systems evolve and move slowly. However, the steady progress has been at a slower pace for some forecasted elements like quantitative precipitation, where more efforts are needed that span from observational needs and model improvements to communication of forecasts. So the convective permitting and explicit convection modeling we talked about relates to the issues of how models are not very good at doing precipitation compared to other things like winds and temperature, for example. This section highlights some key messages and recommendations that were discussed in Brunet et al. That's the WMO report. Although we note that the helpful comments of the reviewers and additional discussions between the authors have provided us with some new perspectives in this summary of the presented as a paper here. As such, guidance must account for uncertainties and society's ability to use weather and climate forecasts. We emphasize optional ways of development and additional considerations, which include economic and operational issues that may need to be applied in decision making. Each section here is long, but I'm not going to read all of it, but it involves it should be, I already misplaced things, I think. This should be policy. So we are going from here to policy changes. In our changing world, the ever-growing need for weather and climate services has meant the value of information is becoming better understood and appreciated. The market growth for NEWP is stimulating a variety of new business models that may fit diverse national and transnational frameworks, improve the quality and access to information, and contribute to robustness and efficiency of the requisite underpinning activities, like environmental monitoring and research. Improved coordination and collaboration among the public and private sectors of the weather and climate enterprise with strong engagement of academia will accelerate the achievement of the vision for improving skill over the coming decade, while technological advances and open data policies have enhanced collaboration between these sectors already. Improved coordination and collaboration remains a fundamental need, with degree of cooperation varying substantially across different countries. So geopolitics matter a lot, trust matters a lot in the Indian subcontinent, for example. The expectation is that each sector will continue in its most relevant roles. At the same time, new potential synergies need to be effectively promoted and implemented. What is on the policy side? Prevailing free and open data sharing among countries and institutions led by WMO has facilitated progress, including the establishment of the Global Basic Observing Network, in which the basic surface-based observing network is designed, defined and monitored at the global level for international exchange. So I won't read more, but you get the idea that they are a good list of ideas. In terms of research and development, the general framework for R&D in an EWP has long been better utilize NEWP forecast data to meet society's needs while serving to reach the theoretical limits of predictability, going back to Lorenz in 1963. Defining this theoretical limit remains a challenge, since the Earth system contains both slowly varying components like sea surface temperature, soil moisture, snow cover and sea ice that can aid predictive skill, and highly nonlinear, rapidly changing phenomena such as convection that can produce both large-scale errors and significant errors downstream on the jet stream due to modification of the Rossby wave packets. Technical terms, if you don't know, you can look up my other podcasts. Efforts to advance predictive skill include increasing high-performance computing capacity, improving observational instrumentation, providing more accurate data with higher temporal and spatial resolutions, advanced dynamical course and better representation of complex physical processes, better model initialization through the utilization of expanding satellite observations, taking advantage of novel new measurement strategies such as crowdsourced data, rainfall from cell phone tower attenuations, and improved utilization of polarimetric radar measurements as models move to kilometer scale, and more effective data assimilation methods, and use of ensembles to represent uncertainty in the initial state and model processes. Sorry for the rapid reading, so many words, but I wanted you to just listen, and you can of course go back and read the paper as well. Looking at some predictability and dynamical and physical modeling challenges, significant outstanding challenges remain in terms of weather and climate predictive skill. Mid-latitude weather regime transitions at the week 3 to week 4 time range, teleconnections between tropical phenomenon such as MJO and mid-latitude synoptic scale weather patterns at the monthly range, seasonal to seasonal scale sea ice cover and thickness predictions, and the different trends observed in the Arctic and Antarctic, and these also affect the monsoon, for example, and even cyclogenesis and so on. Large-scale patterns of precipitation and mid-latitude circulation changes in climate change projections, deep ocean circulation and ice sheet sensitivity to change in climate models, convective precipitation beyond the short-range closure of the water and energy cycle. Model and data assimilation shortcomings include the following: major uncertainties associated with the parameterizations of key processes such as deep convection, orographic drag, cloud microphysics, and aerosol interactions, especially indirect interactions. Thermodynamic and dynamic coupling with Earth's surfaces, including land, waves, snow, and sea ice, and their impact on global circulation. Limited understanding of the possible feedbacks of atmospheric composition on NEWP predictive skill and climate simulations. Mismatching fluxes at the land atmosphere, ocean atmosphere, and ocean sea ice atmosphere interfaces. Lack of data to constrain the models is also a serious issue for fluxes. Insufficient and incomplete treatment of systematic and random errors in data assimilation and ensembling. insufficient use of diagnostic methods for tracing key sources of model error back to their roots in weather and climate models. This is from an older report. So I will stop this podcast here, and we will read the rest of it in the next podcast, because I don't want to make each podcast very long, but you get the idea that the team has considered the history, the challenges, and then the prospects for advancing weather and climate forecasting, which we will look at in the next 1 or 2 podcasts. Okay.